Ahoy, hoy. Welcome to Answer Everywhere. This is an improvised live show where every week, unencumbered by any sort of preparation process, we dive into a code base that we haven't looked at before and try to figure out what's going on. Today, we're taking a look at Docker. I've gotten a bunch of requests to do Docker. Um, and the way I've interpreted it is that we're going to look at the thing that used to be called Docker Engine. Docker is a bunch of different things. It's a corporation and they have several different products. There was a Docker Community Edition, which is now, I think, just rebranded as Docker Desktop. And the software, the open source parts of the software that make Docker Desktop do its thing are rebranded as Moby. And so that's what we're going to take a look at. There are some other projects that are related to Docker, which we may do in the future, things like containerd, runc. But we're not going to take a look at those today, just so that we have this scoped down to something that is somewhat manageable. And then the technology underlying Docker, at least on Linux, is something called cgroups. I'd love to take a look at cgroups, and I'm like 99.98% sure that we're going to do that at some point in the near future. But we're not going to do that in this episode either. So what does that leave us? It leaves us with all of the kind of user-facing stuff from the Docker ecosystem. And this is things like, I believe, building Docker containers, the code to manage layers and images in Docker. And there at some point should be, some sort of server or daemon to respond to command line requests. And then in terms of how far it goes down at the stack, at some point it should bottom out at some calls to probably containerd to ultimately manage the cgroups. And then we're not going to look at anything that would be above this, such as the Docker Compose, I think it's called. We have looked at Kubernetes, which is kind of like a maybe slightly fancier version of Docker Compose. So you can watch that video if you're interested in some of that stuff. All right, so let's dive in. So there's a bunch of stuff here. So this is all in Go, I believe. Yeah, Go, and Docker files and shells. And what do we want to see? I'm not sure. I don't have a sense yet of what's going to be the most interesting stuff here. So here's one way I could go. Ultimately, my impression of Docker is it's going to be kind of like a set of, you could imagine the initial version being a set of like bash scripts to configure cgroups, some version of Linux containers that are a layer lower than most people think of them. And then as you work with containers for a while, you realize that there are these little pain points, that there are these, not necessarily little, but a lot of maybe logistic or supply chain pain points. And that's going to be, I think, where Docker adds a lot of its functionality. And so my impression is that the repo is going to be a little here or there where there's not one single place where all of the cool functionality is. And that may make it a little bit harder to get our teeth around or sink our teeth into what makes Docker go. But we're going to at least, make an attempt at it. So containers should presumably be utilities and libraries for handling, for working with containers. That seems pretty important. Layer, I'm going to guess is important since a lot of Docker is about layers. And my mental model, and we'll see some of this, and maybe this isn't entirely technically correct, but my mental model anyway is that what Docker is really doing is we have to have some way of packaging all of the file system stuff that goes into a container. And so it does that via an overlay system. And there's going to be some logic to build up these Docker images out of images that came before. And that's going to be the layering. And I think overlay is related to that as well. And then there's going to be things like, we want to mount host volumes as part of Docker, or we want to use the host network. So there's going to be some stuff to parse, config, things like parsing the Docker file, and code to assemble all of that stuff. And then there is there are the Docker repositories, which should basically just be some scripts to fetch things, probably by content addressing like SHA-hash. So that's what I'm kind of imagining going on. And hello. And Gustavo is asking, what's the difference between Docker and Moby? I don't know. Okay, you just got here. Yeah, I explained it a little bit. The TLDR is that Docker, in an effort, so Docker, the company, gave away a bunch of stuff because they wanted to make containers happen, is my understanding. And containers at this point is kind of an undifferentiated value add. So they found themselves in a position where they were giving away a ton of free bandwidth in the form of Docker IO, and everyone was using containers, but not necessarily using Docker or paying for Docker. So they kind of took the stuff that was the least enterprisey and spun it off into Moby. And so this is the stuff that you, like if you go to the Docker CE, I think, or the Docker engine, I forget what the repo is called, but it's on the link on this page. If you go to the old Docker repo for the community edition stuff, it basically points to Moby. So that's basically the relationship. One sec. All right. So we've got container and layer. OCI should be the Open Container Initiative. Package, I peeked at before. This is just utilities. Plugins, we'll ignore profiles. I'm not sure how important that is. Quota might be mildly interesting from a technical point of view, but there's so much stuff here that I guess we'll skip quota for now. I'll open registry just to see if there's anything interesting in there. Volume could be somewhat interesting. Vendor might just be vendored code. Yeah, this just looks like dependencies. etcd, I don't know what they use etcd for. That's the distributed key value database that Kubernetes uses. Open census is, I think, tracking like telemetry. Same with open telemetry. And then I don't know what this Uber's Go libraries. I'm not sure what those are up to. Network is maybe interesting. Internal, who knows? Image, a Docker image is a fundamental type. So let's look at that. And that might be enough. I guess command, client, CLI, and builder. That should be enough. Oh, and API. Let's start with API. So in the API, we have not much. Working on the engine API. So it's HTTP API used by the command line client to communicate with the daemon. I don't know what the daemon means in this context. So there's the Docker D daemon, which is, if I understand correctly, so it's managing the like highest level, I guess, of abstraction, and then container D and run C somehow coordinate to manage the actual containers. I think container D is a layer above run C, but it's not easy to find quick answers to those things. So I'm not 100% sure of that. So this is going to be essentially the engine API. And I think daemon here is probably the thing that was called Docker D when this was called Docker. I don't know what it's called now. And we have a server, which I'm going to guess is the daemon, the same thing as the daemon. And this is just, we're going to route some commands and stuff, and we have some HTTP utilities. So worth looking at the server? I don't even know. It should basically be a standard Go server with some middleware potentially. And we've got this create mux, which is often used to handle both HTTP and gRPC, but it might be just used to mux HTTP. I don't know if we have gRPC methods. No, I don't think we do. Okay. So this server stuff is probably not super interesting. Let's abandon it and take a look at if there's anything that describes what the API actually looks like. And the API should really just look like whatever the API looks like on the documentation. We have types, common.go. Is common.go interesting? No, not really. And this Swagger. This is going to be just some description of the API itself. And we'll ignore that for now. Okay, so here's the container directory. And we have a fair amount of stuff. One is env. I assume environment in some sense. Is this just filler? Replace or append env values. Oh, I guess env is like the environment of the container, essentially. And what are we doing with it? We've got some map, and we're iterating over it. It's going to return the default with the overrides either replaced by env key or appended to the list. So I guess we're going to look at what you've configured for the environmental variables. We're calling string index of equal sign. I guess this is a mapping between, foo equals bar sets the variable foo to bar. That seems like just a utility method. We have health, which should probably be just like health checking, health reporting of the server, I would guess. So we have the struct has health and a channel and a mutex. And the health status returns the current health status. Okay, so this looks like just standard server stuff. History.go, a convenience type for storing a list of containers sorted by creation date in descendant order. Okay, so history is just a list of containers, I guess the previous containers. And I guess we keep track of mounts on Windows and Unix. State might be interesting. There might be an important enum here. So the state has a bunch of, instead of being an enum, I think Go has enums. Like, it's been a while since I programmed in Go. Hello, QSM. So we've got a mutex, not surprising. State holds the current container state and has methods to get and set the state. It has an embed, which allows all of the functions defined against state to run against the container. I don't know what an embed is, but we'll see. So the states, I guess you could be running or paused or restarting. OOM killed, I guess killed for running out of memory. Out of memory is OOM. Whether we might be removing the thing. Dead, I forget what dead means, but some version of killed and even worse than killed, I guess. And then there's a PID, which is a process ID that I'm not sure how the Docker process ID relates to the process IDs of the underlying OS, but they are a thing that exists. And then we have things like exit codes. Now, I don't know why we have multiple Booleans, why this isn't some union type. For example, okay, here we go. Paused containers are both running and paused. Freezing the process requires the process to be running. Okay, so the reason they're Booleans is because they're not mutually exclusive. So you can be both running and paused. Can you be running and OOM killed? I don't know. Then we just have some like status struct, which basically just has an exit code and an error. This is all stuff that this is all super like bog standard Google stuff that you would see, for example, in a Google microservice. But they're not using any of the Google types. And I don't believe that they have any Google history in particular. All right, and we can get the state, that sort of stuff. A wait condition. Wait condition not running default is used to wait for any of the non-running states. So I guess if non-running is like, I guess, apparently created, exited, dead, removing, or removed, and you can wait on them. Waiting on created makes sense because you might wait for it to be running. I don't know what it means to wait on a dead thingy container, but you can do it. And then waits until the container is in a certain state indicated by the given condition. A context must be used for canceling the request. A context. Again, we have something that's very gRPC-ish, but I think this is maybe built into Go. I can't remember if this is part of Go proper. The context must be used for canceling the request, controlling timeouts, and avoiding Go routine leaks, not links. Wait must be called without holding the state lock. Returns a channel from which the caller will receive the result. Okay, so wait is going to give you a channel, and the person who calls is essentially a callback via the channel. And you're going to get maybe an error and some other stuff. I guess you'll get the state status that we looked at before. Okay. So that's all fine and good. Store is presumably some sort of storage. Store defines an interface that any container store must implement. You can add a container to the store. You can get a container from what? By an identifier? What identifier? I think these identifiers are just the strings. Like if you have like Ubuntu slash Ubuntu colon latest or whatever, however Docker containers are named. I think that's the sort of identifier it means here, but I'm not positive. You can delete it using the identifier, and you can list the containers. I guess list takes no arguments, so you're just going to list everything that's there. You can get the number of containers by calling size. You can get the first container. I don't know what first means. Maybe it means the first that was added. Doesn't I don't know if there's a natural ordering other than the order in which it was added. And you can apply all. You can take a store reducer, which should operate in theory maybe a little bit like what was it, Redux or React. I think Redux is the one we looked at that has this idea of a store and reducers, and I'm wondering if this is essentially the same pattern. Essentially, this is going to map a function, I guess, over all of the containers in the store. When would you do this? I'm not sure. Occasionally, I guess I'm mildly interested enough to see if we can find that. I think, let's see. See if we can find a call to apply all. Here's, I guess, an implementation of apply all. So this thing is going to, so daemon.go has a call to apply all. Is this going to scroll down? Here we go. Apply all this function, and it's just going to take a lambda that's, I guess, going to, if it's not running, we return. We might log some stuff, and we're going to try to shut down the container and check errors, etc. So this makes sense. We're just going to yeah, I guess if you want to do something on all of the containers on the system, you can just map over all of them. And it looks like you don't map over, for example, just running containers or just healthy containers. It looks like you map over everything that's there. And if it's not running, we just make sure to check whether it's running before we do something with it. That's good enough for me for whatever that directory was. Just double check what that was. Okay, this was container. Is there anything super interesting that we're missing in container? I think we looked at all the interesting stuff. I guess maybe stream. Oh, we didn't look at container.go. That seems pretty fundamental. Okay, so a container is a struct. So a container from Moby's point of view, from Docker's point of view, is a struct that has a stream config. I'm not sure what the stream config is, but it has a state, which I guess is probably the same state as we looked at before, a root, which is the home of the container, a base file system, a RW layer, which I'm going to guess is a read-write layer, an identifier and ID, when it was created, whether it's managed. I don't know what managed means in this context. I guess there could be unmanaged containers. A path, I'm not sure a path to what exactly, but some sort of path. Arguments, a config, an image ID, which is like, if you have, let's use the Ubuntu example again. If you have the Ubuntu container, the Ubuntu image is really what it is. You can run, let's say, like 4 different Ubuntu containers doing different things. They should all have the same image ID, or in theory, they could have the same image ID if you wanted them to, but they would be different containers. And so this is just like a pointer to the underlying image, I think. And then a manifest for the image, which is an OCI spec descriptor. So this is presumably, OCI spec is presumably some external library that knows about the Open Container Initiative spec. If you can find OCI spec. Yeah, so this is just the open containers repo, I guess. Some network settings, which hopefully we will see soon. By soon, I mean by the time we get to all the tabs. And then a path to log to, a name, which is, I guess, different from an ID. Like, I think you can call your container TED, and that's a different name than whatever the official identifier is. A driver, I'm not sure what driver is. This might be the thing like run C, OS. I'm guessing. I'm not sure how cross OS containers work or if they're really even possible, but I guess we record the operating system. And then we have things like how many times have they been restarted? You see these statistics if you list the containers on your system or somebody else's system, whatever Docker you have access to, whether it's been started before, mount points, host config, etc. Okay. And then we have some Unix specific fields like host name path, host path, shim path, I'm guessing. Maybe SHM is something else. I'm not sure. Resolve conf is like DNS stuff. And then we have Windows specific fields like network shared container ID, shared endpoint list, and local log cache meta. Okay, something about logs, something about networking stuff, and shared endpoint, whatever shared endpoint is. Then some security stuff like mount label. Mount label contains the options for the mount command. Okay, so that's, I guess, security in the sense that you don't want to give people access by mounting things improperly. Process label, I'm not sure what that is. App Armor is one of these Linux security. I'm not sure what the official word is, but it's kind of like SE Linux, but simpler. But it's like Linux, like per application security profile stuff. SecComp profile is probably similar. And no new privileges, I guess, is whether you're locking it to adding new privileges, presumably. And we have this new base container, which seems to essentially be a constructor, a Go style constructor that's just going to return a container with a default set. And what else is here? From disk loads the container configuration stored in the host. So I'm guessing this is just reading a file, although there's no file being passed in. So this must know where to look somehow. Oh, no, we're calling it on a container. So the container has knows where its config path is. And we're going to just presumably try to read it by calling OS open and getting some JSON, reading it, closing when we're done, decoding the JSON and getting a description. And then we're going to call deck. I was calling it description, but maybe decoder is the right word. So we're going to call decoder decode on the container and maybe get an error. If we don't get an error, I don't know what has happened. I guess essentially decode is going to populate maybe some fields of container and then such as the OS. And then we're going to check the OS is not empty, etc. Maybe let's take a look at decoder decode just to verify that this does. Well, read. This is log file stuff. I don't know if log is where I want to be. I guess we get decode down in line 192. So let's just wait. And then similarly, you can write stuff to disk. This is basically the opposite function. Checkpoint 2. Checkpoint 2 makes the container's current state visible to queries and persists state. Callers must hold a container lock. So you somehow lock the container and you're going to write all of its state. Probably at least all of the stuff in the struct, maybe stuff other than what's in the struct, the disk somehow, given some store. But I don't know what a view DB is, but we're just going to call container to disk. And that's going to make a deep copy. And then we're going to save the deep copy. And we just really ignored to disk. But maybe let's take a quick look at it since it seems to be the thing underlying the snapshotting. And we just get the config path, whatever new atomic file writer is, some file writer that does something atomically. I guess it's maybe going to write or not write. And we've got some byte buffer and a multi-writer, and we're going to encode, which is presumably the opposite of decode. And then we decode. Why do we decode? We encode the container, and we make this deep copy thing. And we call new decoder on the buffer. Is that the same thing that we wrote? We have buffer here. W is this multi-writer thing. I guess we're just double checking that the thing we wrote gives us like, this is like a round trip check. I'm not sure, but we're returning the deep copy. And return. Okay, here we go. Returns the deep copy. There we go. All right. We've got things like read host config. We use the host configuration from the disk. That's all straightforward. I would like to see decode or encode. Get resource path. That's not so fancy. I thought this was going to be a. Oh no, this is new decoder. Let's find decode. No symbols found. What? What are you talking about? What if I go here? Oh, this is just a call. Maybe it is part of the logging. No, I don't think so. All right, whatever. Actually, let's go back and see if we can find out where. Are we importing decoder? We have encoding JSON. Okay, so the encoder seems, the encoder and the decoder seem to just be the JSON stuff. Is that right? Yeah. Okay. So that's just reading and writing JSON. It's not so important. All right. That's container. That all looks pretty much as you would expect it, I think. No real surprises there. Here's layer. Let's start at layer.go. That seems to be like the place to be. Package layer is a package for managing read-only and write-only. Read-only and read-write mounts on the Union file system driver. The Union file system is like a file system with a bunch of mounts that all seems to be one file system, I believe. Read-only mounts are referenced using a content hash. Okay, so we're doing content addressing really. So you hash some stuff and that gives you a unique identifier and it's collision resistant and all that stuff. And are protected from mutation in the exposed interface. Why protected from mutation? Because if they're mutated, their hash is different. The tar format is used to create read-only layers. Okay, this is actually what I was wondering. I was thinking that under the hood, Docker is really, Docker layers are really just tar archives, and that seems to be literally the case. The tar format is used to create read-only layers and export both read-only and writable layers. The exported tar data for read-only layer should match the tar used to create the layer. I don't know what that means. The exported tar data, you're going to export some data for a read-only layer, match the tar used to create the layer. Yeah? Okay. I'm not sure how it wouldn't, but that seems reasonable request. All right, so what do we got in layer? A bunch of errors, such as the layer doesn't exist. It's not, so sometimes, sometimes I decide to delete random parts of the like varlib container directory or whatever. And you see you see some errors along the lines of the layer does not exist when you try to when Docker doesn't recognize that war has been waged on the underlying data yet. Layer not retained when attempted on a layer which is not retained. I'm not sure what retained means. Maybe it means it's like a temporary layer and it's discarded. Mount does not exist. This is you're trying to mount something that doesn't exist, etc., and so on and so forth. And what do we have? A chain ID is a content addressable ID of a layer, which is just a digest. What is digest? I'm not sure. We should be importing some sort of hash digesty thing. Go digest. So whatever Go digest is using, I'm kind of curious. I'm not sure if it's going to be easy to find out, but I'm guessing some SHA. A digest is just a hash. That's right. The most common use case is content addressable storage systems. The most common use case for a digest is a content. Is that right? That's kind of a crazy claim. I would feel like the most common use of a digest is like just ordinary encryption stuff. I don't know what it means by common. Like most most code repositories, most of the time, a data center is digesting something. It's used. I don't know how they're imagining that being computed, but that is a common use case. All right. Anyway, a hash. Fun, fun, fun. All right, and so we've got this. So here's like a type. I was going to call it a struct, but it's not a struct. We've got tar streamer, which should just stream a tar. An object which may have its content exported as a tar stream. And so we've got a tar streamer, tar stream from chain ID. So you're going to pass it a hash, and it's going to somehow look up the appropriate tar and stream and make it available for streaming. Chain ID returns the content hash of the entire layer chain. The hash chain is made up of diff ID of top layer and all of its parents. So to get this right, you have to have some scheme to make sure that you do it exactly the same all the time. So for example, in theory, it makes sense that like one layer depends on a layer before it. But if you somehow had two layers of equal, let's say they were like directories that were side by side or whatever, you have to make sure that they're in the same order so that when you hash it, they hash to the same thing. And I think that what this is telling us is that whatever diff ID is, we're going to have some chain, I guess, probably like a chain in the sense of like a list that doesn't branch. And we're just going to call diff ID of the top layer and all of its parents. I don't know what top means. Top would seem to be like the one that doesn't have any parents, but maybe top is the child. And somehow I'm going to guess this is done recursively. So we'll see. And then diff ID returns the content hash of the layer. Okay, so this is the essentially the hash of just the tar of. So the current layer is, I guess, some sort of tar. This is the hash of just the tar, and then somehow we're going to chain them up, and maybe we'll look at the algorithm for how they chain up. Parent returns the next layer in the layer chain. So this is the parent. I guess top really is child. I'm not sure. Then size is how long is the layer chain? Diff size returns the size difference of the top layer from the parent layer. And then metadata returns the low-level storage metadata associated with the layer. The low-level storage metadata. Maybe including things like path? I'm not sure. I don't know what other exciting metadata there is. And then we have read-write layer, which has a lot of the same stuff, including parent, some stuff about mounting, the file system path to the writable layer. Okay. This is where I guess you can write stuff. Unmounts the RW layer. This should be called for every mount. If there are multiple mount calls, this operation will only decrement the internal mount counter. All right. And then we have the ability to apply a diff. Then here's metadata stuff in the metadata for read-only layer. So up here we were in read-write. Here's some read-only stuff. You have chain ID, diff ID, size, diff size, basically the same sort of stuff. Mount init. Mount init is a function to initialize a writable mount. Changes made here will not be included in the tar stream of the RW layer. All right. Create RW layer opts contains optional arguments to be passed to create. So these are just some options like mount label and a function to initialize stuff, some storage options. And store, which is a different store type than the one we saw before, a backend for managing both read-only and read-write layers. A register, which I'm going to guess is like the Docker registry. And we can get a layer from the chain ID. We have a map from chain IDs to layers. Makes sense. We can release a layer. And that's going to return some metadata. Not sure why. We can create a read-write layer, get read-write layer, etc. and driver name again and driver status. Again, I'm not sure what they're calling a driver yet, but we'll probably see something driver related. To create chain ID, if you give it a list of diff IDs, we'll call create chain ID from parent, starting with the empty string, and then passing in the digest as a variable length argument. And luckily for us, here's the implementation. We are just going to check that if you have no digests, we're just going to return parent, which in this call is the empty string, right? Okay. And if parent is the empty string, we're going to call create chain ID from parent. I guess like recursively, right? So we're redoing the call and we're popping off the first digest by calling digest at 0. And then we're passing into the variable arguments the remainder of the digest. So this is, I think, what I speculated above. We're just recursively calling this hash function and like walking down the list. And the thing that I had mentioned that you have to make sure that things are in the same order, and the reason is this. So if digest 1 and digest 0 switch, then this is going to give you a different hash. And at any rate, we that gives us this. All right, so if parent is empty string, which it is here, then we're going to call this recursively, and it's going to just return. And then if we get down here, then the parent is no longer the empty string. The parent is like digest of 0 or something else. And we're going to call digest from bytes of taking the parent string, casting it as a list of bytes, and similarly with the digests at 0, and then calling create chain ID from parent with chain ID of digest and the rest of the stuff. I'm not quite sure what this part is doing. Hey, whoa now. Yeah, where was I? Somewhere around here. So h is equal to h n minus 1 dot 256 of n. So h is maybe hash is equal to the hash of the n minus first. Didn't this depend on n? Maybe this. I'm not sure what this notation is supposed to be. I think this is some way of indicating this the recursion relationship. What I don't know is the difference between here and here, because if we're here, then we just call chain digest without the string stuff. But I guess we were passed in a string in this case. And what even is a chain ID? Is a chain ID just a string? In this file, chain ID. Okay, so the chain ID is just a digest, which we saw before. So I'm not really sure what's going on here, but it's I think this is one of the like end cases of the recursion somehow. And we're taking this stuff and creating a whole string out of the parent and the first non-parent digest. We're taking that whole thing and making it a list of bytes, and then passing that in, and then calling the same function and passing that thing in as the first. Why? I don't know, but that's how it's done. Release and log is just releasing some stuff, and then log release metadata. We call release here. Did we see a definition of release? We see that as a thing. Maybe it's implemented in different different subclasses. I don't know. All right, is there anything else cool in layer? Whoa now. We have layer Unix, layer Windows. Those are probably not so interesting. Migration, maybe these are for changes in layers. Checksum for graph ID. Parent, old tar data path, new tar data path. So this is for, you might have done something that changes the tar data, and somehow they're gonna figure out what the appropriate hashing is. Then we have stuff like mounted layers, empty test. I guess empty layer, a file store. Let's look at a file store, at least very quickly. A file metadata store. So this is storing, I guess, just the metadata, or is it also storing the layer data? New FS metadata store returns an instance of a metadata store which is backed by files on disk using the provided root as the root of the metadata. And things like get, let's take a look at get layer file name. You're going to give it a chain ID, which is basically a hash, and a file name, which is a string. And you're just going to call file path join on get layer directory on the layer. We're going to find out from the chain ID where its directory is, and then we're just going to like put slash file name, I guess, at the end. And to get the layer directory, we're going to give it the chain ID. We're going to digest the layer. We're going to hash the layer essentially. And we're going to, the location is like the root of the file system slash take the hash, find out what algorithm it is, like SHA-256 or whatever. That'll be the first part of the directory name, I suppose. And then the actual hash itself will be the second part of it. And that's the file name. All right, cool. So that's layers. OCI. OCI is small. We have caps. What do caps be? Utils, defaults. Cap, set GID. Oh, maybe capabilities. Yeah, capabilities. Returns a Linux kernel default capabilities. Okay, so that's fairly low level stuff. Got some fuzzing, some defaults. I guess let's just look at OCI.go. To do, verify if this regex is correct. For A, all. Seems like for something as fundamental as Docker, you'd want to really make sure that the regex is correct. The docs at Torvalds Linux, this is the Linux source code. All means it applies to all types and all major and minor numbers, and shows an example that only passes A as value. Would be the implicit equivalent of A colon RWM. I don't know what that means. Oh, it's a cgroup thing. So this is some cgroup regex. We're dealing, Docker is ultimately, in my gloss of it, managing cgroups. And so that's that. And we could do things like set capabilities, append permissions from cgroup rules. So this is cgroup stuff. And can I close this panel here? Yeah. So append device permissions from cgroup rules. Takes rules for the device's cgroup to append to the default set. You're going to have some device permissions, a list of device permissions, and a list of rules. And then you're going to return some cgroups in an error. Cool. Phew. Hey, Doraj. I'm excited too. This is fun so far. So actually, since we found the first instance of cgroups, let's ask, I guess, Bard. We haven't seen Bard in a while to tell us about cgroups. So the TLDR is that cgroups are a way of I think initially they were designed to just hierarchically group processes in Linux, so that if you change something, so when you, like, for example, fork, you want to stay within the same process group, and you want to be able to, if you're, say, Google, and you're running a bunch of services, like one service might be search and another service might be Gmail, And another service might be maps. They might have different characteristics in how they, deal with data, what their cache behavior looks like, what their memory access looks like. And you want to be able to run all of those things on the same physical machine, and say like we want to apply these settings to maybe just the map processes, and anything that, if maps creates a new process, we want the same restrictions to apply to that. So it's a way of doing these hierarchical groups. But in addition to just having these hierarchical groups, there's also stuff like um, isolation, which I believe that containers are not considered a security boundary, and you shouldn't use them as a security boundary. Maybe that's changing, I'm not sure. But things like isolation and all of the containery stuff that we have come to know and love. But let's ask Bard for an overview of cgroups. Give me an overview of cgroups. Cgroups in Linux. So there's short for control groups, a Linux kernel feature that allows you to manage resource usage, CPU, memory, disk I/O, network, etc., of a collection of processes. This means you can set limits on how much of a particular resource a group of processes can use, or you can prioritize one group of processes over another when there's resource contention while you see groups, preventing runaway processes, isolating resources, enforcing resource quotas. How do they work? They're organized into a hierarchy, with each cgroup having a parent cgroup. A cgroup's resource limits are inherited from its parent cgroup unless they are explicitly overridden. This allows you to easily manage resource usage across a large number of processes. There are many different cgroup controllers, each of which controls a different kind of resource, and such as CPU, memory, block I/O, net devices, and devices. All right, that's great. Thank you, Bard. All right, so that's cgroups. And this is part of what OCI is doing. And there's not much here. We're just setting permissions. And all of the real cgroup stuff should be handled by containerd, I believe. Here's registry. Registry should, I think, is just going to be Docker registry, which we all know in our hearts is just like an AWS S3 bucket. So I don't think there's really much especially interesting going on here. But we have auth, which is just going to be authentication, authorization. Auth client ID is equal to Docker. And we've got some login credential store, which is a registry.auth config. Where are we storing it? I don't know. Are we just storing credentials on disk? I hope not. And static credential store, etc., etc. Anything interesting? Login v2. I guess login v1 wasn't cutting it. Login v2 tries to log in to the v2 registry server. A given registry endpoint will be pinged to get authorization challenges. These challenges will be used so these challenges will be used to authenticate against the registry to validate credentials. Okay, so we're just going to try to authenticate, and presumably we get back some sort of token, right? We get back 2 strings and an error. And what are the... if we get down here, we're getting the empty strings. We might get a status code. And if we get a successful status code, we are going to return login succeeded as a string, the identity token. So we do get a token, and nil as the error. Okay. So standard login stuff. Search.go. This should be registry search, I guess. So accepted search filter tags is automated. I guess that's for like a bot or a tool that might sometimes search. Is official. I'm not sure what that means in stars. I don't know what stars is. Maybe that's like you can search for Things that have a certain number of stars on Docker IO? I don't know. Search will take a context, some search filters, a search term, a limit, authorization, and what else? Go people don't believe in the need to have short lines. Their code just goes on and on and on. All right, headers. And we're going to return a list of registry search results. And we begin by validating the accepted search filter tags. What are these are the things we saw before. Is automated, is official, and stars. And then we call search filters get bool or default is automated. This is automated field is deprecated. Reset the field for the next release. All right. I don't know what this is automated as official stuff is. And if it contains stars, then we're going to range has stars. I'm not sure what stars is containing, but we're going to iterate over some stuff. Convert a to I to convert to an int, right? And something, who knows? I guess we're looking for things that have a certain number of stars is what I'm going to guess. We've got this search unfiltered thing. I don't know what it is, but and then we've got more search result stuff. I don't know where we actually look for things. Maybe that's search unfiltered. In this file, this is definition 83. Search unfiltered. So search is a long-running operation. Just lock s.config to avoid blocking others. We're gonna lock some stuff. I guess we're gonna just look at an index, and then we're gonna unlock it. And if index.official, if pool library foo, it's stored locally under foo. I guess maybe official means like first we're gonna search locally, and then we don't search locally, we'll search the official storage. Is that the idea? At any rate, we're gonna look in some index, and we've got, so there's this prefix thing in Docker that behaves a little bit oddly, but maybe the reason it behaves oddly is that we call string prefix here. So they want you to be able to say like pool Ubuntu, let's say, but really you're pulling like Ubuntu/Ubuntu, I think is the sort of thing that it's doing. And whatever new v1 endpoint is, I guess this is some model for the HTTP endpoint for the registry. And we're getting an HTTP client. We're going to try to authenticate. Check the identity token if we have one. And if we don't, we're going to look in the credential store and set some headers, including the user agent. And it's just a call to the, this isn't actually doing the search, I guess. This is really just calling the repository and asking, and like calling a search endpoint, which is not so exciting. Okay, so that's search. All right, and then we have search endpoint. Is that more exciting? I don't know. New v1 endpoint parses the given address to return a registry endpoint. All right, so that's just parsing the address, getting an endpoint. Here's, I guess, ping for pinging the server. Trusted location. And some stuff about requiring headers. All right. Registry, did we look at registry.go? Not sure if we did, but let's take a quick look. We've got things like host certificates, TLS, more certificate stuff. Some stuff about transport. New transport returns a new HTTP transport. If TLS config is nil, it uses the default TLS configuration. Okay, so this is just essentially HTTP client stuff. And we have service. Service is a registry service. It tracks configuration data such as list of mirrors. All right. We've got some locking stuff, authentication stuff, contacts the public registry with the provided credentials and returns OK if authentication was successful. Resolve repository splits a repository name into its components and configuration of the associated registry. We have an API endpoint, which has a mirror, a URL, a version number, whether it's official, etc. Lookup pool endpoints, just calling S, lookup v2 endpoints, etc. Cool, but where's the stuff? Here's the function for computing the v2 endpoints in v2 service.go. And that's about it. See if I can find some stuff about index. Oops. I'm guessing that the index isn't so hard. You just keep a list of all the I guess images, and probably about it. And some metadata. I'm not sure. Container view. Where was that? Let's look in search. We saw some reference to index. New index info. Oh, it's in registry config.go. New index info returns index info configuration from index name. We're going to validate the index name, return any configured index info first, and then construct a non-configured index info. And the index info just has a name, mirrors, and that sort of stuff. Yeah, okay. Well, I don't know where it actually searches stuff, but maybe it's just iterating over some list of things. And we can, if I'm still curious about it, we can check in more later. But here's libnetwork. This should be a bunch of stuff. For example, as you're setting up the containers are communicating with each other over some network. Imagine in a lot of cases, basically just Unix sockets for Linux. But the network is pretty configurable. So this is probably a lot of there's a lot of detail here, and I don't think we're going to benefit a huge amount from going into the detail. But let's at least pick and take a peek at what's here and see if there's anything that really stands out to us. Store is probably just going to be reading network stuff from the storage, given the stuff we saw before. Get networks. So controller get networks is going to get the store and I guess read stuff from the store. We're going to look up, I guess, given some key, network prefix. Okay. This does seem to be just reading stuff from disk. Where I saw a network.go. Let's look at that. Network.go. DNS backend represents a backend DNS resolver used for DNS name resolution. So yeah, this is, I know in Kubernetes that Kubernetes has its own DNS system. And I imagine Docker is basically doing the same thing because the containers need to have some way of referring to each other. But I'm not sure. We'll see what it says. So the DNS backend resolve name resolves a service name to an IPv4 or IPv6 address by searching the network sandbox. By searching the network sandbox is connected to. Okay, so this is resolve name. Searching the network is the sandbox is connected to. Okay. Resolve IP returns the service name for the passed in IP. Resolve service returns all the backend details about the containers or host backing a service. Purpose is to satisfy an SRV query. And then we can exec func allows the function to be executed in the context of the backend on behalf of the resolver. I'm not sure why. N.set queries the backends n.'s DNS option settings. And handle query response passes the name and IP from a response to the backend. All right. And we've got some constants, like I guess we're going to use port 53, which is the default DNS port. This pointer IPv4 domain, I'm not sure what this is. ARPA is the internet thing. I'm not sure if this is standard stuff. I don't know enough about the DNS spec. And then time to live for the response. Maximum number of external servers to try is 3. Next, the IoT timeout. I'm not sure what IoT is. Oh, sorry. It's not IoT, IO timeout. I guess external IO timeout. Max concurrent is maybe the maximum number of concurrent queries that are allowed to be live at the same time. And then how often are we going to log? All right. Thanks for coming. 3:30 a.m. That's late. You need some sleep. They've got this resolver thing. Is the embedded DNS server in Docker. Okay, so they have their own DNS server thing. It operates by listening on the container's loopback interface for DNS queries. So I guess the container, maybe each container will respond to DNS queries. And this is just configuration stuff for that. And we can create a new resolver, some log. We've got the setup function. Returns the setup function that should be run in the container's network namespace. Okay, we can stop the resolver and presumably also resolve things. Handle MX query. I'm not sure what an MX query is, but that's DNS style stuff. Is that resolver.go? Does that mean to go to network.go? Did we go do this? Okay, here's network.go. We have an endpoint walker, which is a client provided function which will be used to walk the endpoints. When the function returns true, the walk will stop. So this is, I'm not sure what an endpoint is in this definition, but this is going to visit the endpoint into something until something is true. Will Smith, I assume the rapper, is saying that this code is much better commented than most large code bases I've seen. Yeah, this is pretty well commented. That's very true. And Happy Day App is saying, Docker is a huge code base and Go is quite readable, I think. Yeah, I think Go tends to be readable. And I think that one of the things that the Go community does well is have lots of standards that are just like sane standards. And I think in a lot of cases, they're basically the Google standards that were institutionalized as part of the language. And so you do Go code is rather readable on its own, but there's also like a lot of uniformity and nice behavior from Go developers. That's kind of like part of the official community. I think Go does that really well. We've got this endpoint walker function, which is a little bit interesting. I'm not sure if we're going to see usages of this, but I'll keep an eye out. So IP info is a reverse mapping from IP to service name. Serve the PTR query. Okay, so you give it an IP, it's going to give you a service. So basically, you're resolving, kind of like DNS. Service map entry is the body of the element into the service map. The IP is a string because the set matrix does not accept non-hashable values. I don't know what that means, but I guess I don't know what a hashable value is. I think most digests operate on strings. So it's a stringified IP. But what set matrix is, I don't know. And then we've got service info and has a service map with a set matrix. Maybe set matrix is a kind of set. I'll check that out. So a service info has a service map, an IP map, and a service. I don't know what a Docker service is. Let's look this up. Let's look up this matrix thingy. Libnetwork internal. This is a different repo. It's in Docker. Oh, you don't get to see it. Set matrix and then Docker service. I'm guessing a Docker service might be a little bit like a Kubernetes service. Unity 3D set matrix. That's something about modeling things. Let's try set matrix Docker. Matrix Synapse. That's the matrix chat thing. Matrix.org. I don't know. Set matrix. Okay, so Docker service. This command works with a swarm orchestrator. Okay, so this seems to be a Docker swarm thing, which would make sense. But is there, what's the difference between a Docker service and Docker container? In short, a Docker service is used mostly when you've configured the master node with Docker Swarm. This might be just a Swarm thing. I don't know. Does anyone know what Docker services are about? Let's ask Bard about, in Docker, what is set matrix? I'm gonna guess it doesn't know. Oh, it does know. Set matrix is a Docker command that is used to set the CPU and memory limits for a container. There we go. It's a low-level command that's not typically used directly by users. Instead, it is used by Docker internally to manage the container's resource usage. So you would call Docker set matrix, container CPU memory. This is basically like peeking under Docker and trying to get more directly at the CPU, C group functionality, right? So one of the ideas of C groups is that you can do things like set limits for a process group. And set matrix seems to be a way to do that via the Docker command line. And we couldn't find it online. And so just to reduce the probability that Bard is hallucinating, let's ask ChatGPT. ChatGPT says there's no such thing. But who's lying? Who's lying to me? I'm going to guess that that Bard is right. Seems like a plausible thing. That means set matrix? Oh no. I don't know. Okay. All right. So that might be what set matrix is. It might be a dirty lie. We've got some stuff for marshalling and unmarshalling JSON. We've got a network struct, which has a controller. I'm going to guess is like the network card. The network type. I'm not sure what type is. Maybe like whether it's a bridge network or something else. Some labels, scope, network data scope. Who knows what that could be? It could be all sorts of things. All of them useful. Whether things like IPv6 and IPv4 are enabled. A DB index. DB exists. I'm not sure what that's about, but it's something. Whether to maybe, I guess, persist the network once the container is gone. Something about persistence, internal, attachable, in delete, maybe is about whether the container or the network is being deleted as we speak. Whether it's attachable, an ingress. I don't know if that's similar to like Kubernetes ingress, like whether you are listening on a port that's visible outside the network, a load balancer IP, and a mutex. I have a feeling that some of this is mainly for Swarm, but maybe not. I don't know. See if Swarm is mentioned at all. Scope.swarm is Swarm node. Yeah, it seems pretty swarmed up in here. Okay, so that's network.go, sandbox.go. Possibly interesting. Sandbox option. This is a standard Go way of doing options. It's kind of like functiony thing. We've got this process options function, which is going to take a bunch of options as variable arguments and set them all. Sandbox struct is a thing that has an identifier, a container ID, controller, etc. And more DB exist stuff. But how did it actually implement it? I guess Docker doesn't really implement. I'm not sure if Docker actually implements the sandbox itself. Maybe the sandbox is just implemented by the kernel, and Docker is just managing it. This delete function looks like it is large. Okay, so let's look at it since it's pretty large. So delete whether to force it or not. So we lock some stuff. And if we are, I guess, already in delete, we unlock it and say another sandbox delete is in progress. And then we set the delete flag, the in delete flag saying that we're being deleted. And then we unlock. Why do we unlock? Set the in delete flag. This will ensure that we don't update the store until we've completed all the endpoint leaves and deletes. And when endpoint leaves and deletes are completed, we can finally delete the sandbox object altogether from the data store. If the daemon exits ungracefully in the middle of a sandbox delete, this way we will have all the references to the endpoints in the sandbox so we can clean them up when we restart. All right, that's that we don't, we won't know like what to delete otherwise, I guess is what it's saying. So we set C to be the controller, the SP controller. I don't really know what SP stands. I guess sandbox. Makes sense. Then we will detach from all endpoints. We're going to iterate over the endpoints and somehow detach. We're not forcing and the end. Okay. This might be automatic. Otherwise, we'll get the network from store and check if we're in swarm mode. If we're not forcing, then we'll call leave, which should, I guess, gracefully leave. What if we are forcing? I'm not sure. And then we call delete. I guess delete is what happens if we are forcing. We never leaved. I'm not sure. I'm not sure if I'm reading this right, but it seems like even if we are forcing, wouldn't it be better to try to leave gracefully first, and then delete only if we have to? I'm not sure. If we're supposed to retain, then we do some stuff, except in delete to false, with some locking and maybe some logging, and then container is going away. Path cache and Etsy hosts is most likely not required anymore. Drop it. So we're going to call Etsy hosts drop of the host's path from the sandbox. And if resolver is not nil, we'll stop the resolver, which is the DNS thingy. And the OS sandbox, maybe that's like a top level sandbox for the whole OS. If it's not nil and we're not using the default sandbox, then we'll destroy it. And then we delete the sandbox, I guess, from the store. Or we delete the whole store. I think we're probably just deleting the sandbox from the store. And then we lock. And if we're in ingress, we set the ingress sandbox to nil. Then delete the sandbox altogether, and then unlock, and then return that there's no error. Okay, that tells us a little bit about sandboxes. We can marshal JSON. We've got endpoints. Endpoints returns all the endpoints connected to the sandbox. Okay, I'm not seeing anything that looks like it's actually an implementation of the sandbox itself, but I'm guessing that's handled either by the OS or by some other component. Resolve service returns all the backend details about the containers or hosts backing a service. Its purpose is to satisfy an SRV query. So this is just DNS stuff. I'm curious if, yeah, so I guess the DNS query is scoped to the sandbox. So maybe that's part of the sandboxing. And resolve name. So maybe that's part of this. Maybe the way that the sandbox works is largely via things like making sure that resolution happen only within the sandbox. I'm not sure. And okay, so is there anything else interesting? So there's firewalls. Those might be mildly interesting, but I'm going to ignore them. An endpoint, I don't know what an endpoint is. So look at it. An endpoint represents a logical connection between a network and a sandbox. You have a network and a sandbox, you're going to connect them. Sounds good. So I guess a network joins a sandbox. Is that the idea? Marshall JSON. Let's look this up. Maybe Docker endpoint. Oh, maybe just Docker endpoint. I don't believe that DuckDuckGo is going to include endpoint unless I really tell it to. I'm going to click on this DuckDuckGo and endpoint will not appear. Okay. But what is it? Let me go back up. So we've got Kubernetes, we've got swarms, whatever Docker context is. I'm guessing an endpoint is somewhat like a Kubernetes endpoint. This shows you how context make it easy for a single Docker CLI to manage multiple swarm clusters, multiple Kubernetes clusters. Okay, this is Docker. This is like Docker trying to compete with Kubernetes, I guess, by making Docker a way to manage Kubernetes and do Kubernetes-like things with Swarm. I'm not sure which came first, but that's kind of how I see this stuff. And I've said some of this before, but maybe it bears repeating that so Kubernetes is essentially a rewrite from scratch of the Borg, the internal Borg cluster management system at Google. And cgroups, the thing that's underlying the Docker, the idea, like the implementation of containers really was a thing that was originally made for Borg and then contributed to the Linux kernel via Google developers. So the original Docker idea, I think, for the startup was to kind of make that kind of technology available to everybody, which eventually they did. But I think maybe one of the problems they ran into as a company was that Google also had that idea and they had just more resources and they had kind of invented a lot of the technology. And I think, but I'm not sure that like the ideas of cgroups go back to maybe other versions of Unix, like Solaris. I think something like Solaris had like zones or some other way of organizing groups. And so I don't think it's the case that Google like invented any of that from nowhere. So all of this stuff has a lineage, but I think the lineage is pretty direct in the case of things like cgroups, containers, Docker, Kubernetes, all that stuff. All right, so endpoint has something to do with, I'm going to think of it as like a Kubernetes endpoint, which I have a mental model of. Maybe you don't. Maybe you've used Docker endpoints. I'm not sure. Controller, I don't think we've looked at controllers before. But let's at least look at one. Package libnetwork provides the basic functionality. So here we get the package level comment in controller. Maybe that's the general theme in these folders. The basic functionality and extension points to create network namespaces and allocate interfaces for containers to use. So the controller, based on what they're writing, this is going to be the thing that like when you send a command line argument like Docker create network or whatever it's called, it's going to be the controller that where the logic to actually create that stuff is either implemented or at least that's the entry point, I'm going to guess. Maybe similar in spirit to like controller in the sense of model view controller. So we get things like create a new controller instance, create a network for containers to join, and that sort of stuff. Controller is a struct. It's got an ID, a driver registry, I guess. Whatever DRV is, IPAM registry, sandboxes, storage, an ext key listener. I don't know what ext means. An agent. Not sure what the agent is doing. And yeah, this looks very control-y in that sense. Let's look quickly at agent. I'm guessing an agent is that kind of like a sidecar? An agent has a network DB, so a network database. Maybe that's what the DB stuff was before. A bind address, an advertisement address, a data path address, court cancel funcs, and driver cancel funcs. What does an agent do? You run your agent in Docker. I think that's using containers as build agents. I think it means an agent in the sense of like a build agent or like a container that like runs and sends metrics. But I'm not sure. I'm not going to dig into too much. Handle key changes. Encryption key. Maybe this is like for TLS stuff. You get a driver. I thought maybe I saw a driver. We have a driver API and drivers. We have driver.go. Driver.go. Okay. Is driver API like a plugin? Network plugin endpoint type represents the endpoint type used by plugin system. Seems to be something related to plugin. Driver is an interface that every plugin driver needs to implement. Okay, so this is plugin stuff. Network allocate invokes the driver method to allocate network specific resources. Network free, delete network, all that stuff. So this is just some API for your plugins to implement. Okay. Here's Moby internal. There's things like mount tree. There's going to be for mounting all of the things for layers, I guess. A test suite, some test utils, tools, unshare, mod, and compat context. These all look pretty unessential. Maybe cool and important, but more like utilities than fundamental. Here's image. What do we have left? We have command. I'm going to ignore command because given what we've seen, that command should basically be just like front end. Like there's going to be some command line utility, and it's going to send commands, and it's going to hit some endpoint. You're going to do stuff, is what I'm going to guess. Client. I'm going to similarly ignore client. I bet we're about over an hour, right? An hour 24. Yeah, so I'm going to ignore client because for essentially the same reason, and then also ignore CLI. And that leaves us with image. An image should be relatively straightforward. We're going to have some sense of the Docker file. I'm not sure if that's an image in particular, but we're going to the image is going to package a lot of the stuff that we've seen already, and then give us a way of manipulating that package in a convenient way. Let's look at image.go. We see tar export. I see a tar export folder. Makes sense because everything is ultimately tar archives, it sounds like. And we have the content addressable ID of an image. This is some hash. Here's some more digesty hashy stuff. V1 image struct. We get a V2 image. Maybe just V1 image. An image has a parent, which makes sense, but only a single parent. So I guess it's a list and not a tree. A comment is an optional message that can be set when committing or importing an image. It's got a created timestamp, a container string is the ID of the container that was used to create the image. So this is like in the Docker file, I guess you might be like from Ubuntu or from Alpine or whatever. I think maybe that's what it means by the container. The container config is the configuration of the container that was used. Docker version author. I guess it stores information about who their author is. I'm guessing it means like the organization rather than the specific developer. And then some config. The configuration of the container received from the client. I don't know how this is different from the other container config, but some more config stuff. Architecture is the hardware CPU architecture that the image runs on. So like, does it run on like AMD 64? Does it run on ARM? Does it run on Spark? Variant is the CPU architecture variant. Presently, ARM only. I guess ARM is pretty heterogeneous, I think, compared to like x86 or AMD 64. So I'm guessing maybe that's why it has variants. In the operating system, it is built to run on like Mac, Windows, Linux, and then the size. That's all relatively straightforward. And then the image is different from the V1 image. In that we've got some root file system stuff and history, which contains things like the layer IDs, the OS version. It's built on some raw JSON. You just shove some JSON in there. And a computed ID is the ID computed from the hash of the image config, not to be confused with the legacy V1 ID in V1 image. And details, which is just more JSON. And the details are things like references. I don't know, references to what? Maybe people who like the image, you can use them as references. We have a size. We've got some more metadata, a driver. And driver might be, we'll see if there's a driver like go here. Driver might just be like plugin API again. And stuff for handling JSON. And that's really about it. And various like helper methods for dealing with it. New child image. The new child image should basically take an existing image and make a child, set it to parent, and add it to history. New history. Okay. Yeah, that's relatively straightforward. File system, is that going to be cool? Store is not going to be cool. Tar export. Do we look at any of this stuff? I guess. Let's look quickly. All right. So file system is just storage. You can walk. This is some sort of for maybe walking the chain of images. You can set delete, you can set metadata, create a new file system store. Walk calls the supplied callback on each image ID in the storage backend. Yeah, okay, exactly. So I think we're just a list, right? Somewhere we should see something like, okay, so we're going to iterate, we're going to range over dir. Where did dir come from? I'm going to read, I guess we're just iterating over everything in the directory. Is that right? Getting digests, validating, and calling f on the digest. So we're passing it. The f is a thing that takes a digest, I guess, as an argument. All right. That's relatively straightforward. Tar export. This is for like loading and saving the images, I think. And there's not a lot there. Okay. Then spec. Docker image specification. So this is the specification. Is this all like Markdown? Okay, so this is like a written, essentially design document for what the images do and specifying so that if you want to implement something compatible, you can implement it on your own, for example. Or if you just want to know how it works, you can read it. Then we have image v1.go, which is, I think, the version we just saw. And this is a lot of the similar stuff. Create ID, history from config, and so on and so forth. Okay, I'm going to call that the end. Docker, as Happy Day app said earlier, Docker is huge. It's a pretty big code base. But one thing we saw was that a lot of the directories look very similar. They have a kind of parallel structure. And once we began looking at what the different things we're doing, a lot of the functions are kind of like things like getters and setters and like read this thing from the disk and write it to the disk. And there's not a lot there that was like a like super powerful algorithm or like an amazing data structure, as opposed to, for example, Redis. We looked at, it was like all novel data, not necessarily fully novel, but all like custom data structures all the time. This Moby, this version of the Docker engine, a lot of it's maybe like you might consider it like scaffolding, a way of providing structure to what you're really trying to do, which is to manage the underlying containers. And so I'd like to look at cgroups in the future so that we get a sense of like what's actually going on in the kernel to manage this stuff. And then, as I mentioned before, there will be some things like containerd and runc that are going to be in charge of, like, if your container accidentally dies and it's supposed to not have died, restarting it, and just kind of keeping a watchful eye over the containers in a low level way. So that's Docker.